Two facts. Fact one, developers who use Ruby love it. Year after year, Ruby ranks among the most admired languages in developer surveys. It's expressive, readable, and optimized for developer happiness. And it's one of the most token-efficient languages too. Fact two, more developers have picked up Go since 2020 than the entire global population of active Ruby developers today. But shouldn't it be the other way? Ruby's expressive and high-level syntax is supposed to attract developers. Oh, thank you. Maybe it's just not enough on its own? What if there's something else that prevents Ruby's well-deserved growth? Let's for a moment forget about incredibly stable 10-year-old Rails code bases. How do we win developers and companies back? How do we improve the ecosystem so that it can support developers in building a variety of workflows without telling them they don't need it? Yeah, probably not like that. We've already tried. Let's try something different. For me, this different is expressed by the Rage framework that I've been working on for several years now. Multiple principles serve as a foundation for the framework. For example, async IO by default. It's not an add-on, it's the core. Every web app talks to a database, calls an API, reads from a cache. There's no workload where non-blocking IO doesn't help. High performance. It means providing you, the developer, with a performance safety net. It's the confidence to ship a complex feature or to handle sudden traffic spike. And it's also about benchmarks. When a team is choosing a technology, many of them evaluate benchmarks to understand the limitations of the technology they're about to invest in. If Ruby doesn't show up well, the conversation ends before it starts. Performance is marketing too. Ease of adoption. If you know Rails, you can write Rage. The goal is that switching should feel boring. And API only, because trying to be everything to everyone is exactly the problem I'm going to talk about. Rage focuses on doing one thing well, leaving a very different concern of the presentation layer to specialized tools like React or Flex. But the principle I wanted to focus more on has to do with hidden complexity. There's this new approach to building software where the developer gives up control of implementation details in exchange for speed. We worry less about the code, but get to ship faster. Many developers oppose it because you end up with a code base you don't fully understand. Debugging becomes archaeology, and when things break, you're stuck. I was talking about Rails, but you were thinking of something else, weren't you? We oppose vibe coding because we know that engineering requires understanding the system. We know that if we can't see the complexity, we can't control it. We can't maintain it. Yet, for 20 years, we've treated our primary web framework the exact same way. We let it hide the complexity from us and vibe code our database queries, our object mapping, and our threading. Both Rails magic and vibe coding rely on opaque abstractions. They hide the implementation details from you. You hand over control to an external agent that builds solutions based on the training data or Basecamp's operational model. In both cases, the developer is abstracted away from the machine. They encourage you not to think about threads, fibers, memory, or network I/O. And here's the irony. AI tools are making explicit code easier to write. We're already seeing it. Tools like Minitest are having a revival because agentic coding eliminates the boilerplate that made them harder to use in RSpec. The trade-off that justified Rails magic 20 years ago is inverting. I'm not saying that Rails is wrong or that vibe coding is bad. I'm saying that if your argument against AI-generated code is, I need to understand my system, then you should hold your framework to the same standard. And that's the space I think Ruby should grow into. Tools that give you power and transparency. There's another side to externalized architectural decisions I wanted to talk about. Let's do a quick thought experiment. Imagine DHH makes Falcon, hell, even Rage, the default solution tomorrow. If you migrate the next day just because of that announcement, you wouldn't be migrating because you evaluated the trade-offs, ran benchmarks, or understood how Firebase handle concurrency better in your specific workload. You'd be migrating because you outsourced your architecture. And it works both ways. If we just accept that Rails is enough, we'll sleep on genuinely better specialized solutions, whether it's Falcon, Rage, or something else entirely. This might sound a bit abstract, so let's make it concrete. Let's look at active job as an example of how Rails and Rage's approaches differ. Active job promises to support you any way you need it, any workflow, any backend. It's a perfect example of an opaque abstraction, one that tries to hide the nature of the underlying system. The illusion here is that the background job that's running in memory, one that runs in Postgres, and ones that runs on Redis are functionally identical because they share the same interface. But when a framework implements an adapter layer, it inherits hidden complexity. It has to translate generic commands into specific backend realities. And if you use an adapter layer, you let the framework decide your architecture. Rage also has a background processing system that's called Rage Deferred. It's a zero setup in-process queue that utilizes Rage's fiber model and uses an on-disk write-ahead log for persistence. No abstractions, no adapters. This is what I like to think of as opaque abstractions versus transparent constraints. Rails says, I can be anything you want. Just plug in the right adapter. Rage says, I'm a tailored, optimized tool for this exact use case. If you have a different use case, use a different tool. By rejecting generic abstractions, Rage invites you to make explicit architectural choices. It doesn't pretend to be a generic queue. It tells you exactly what it is. An in-process, fiber-based queue with a disk write-ahead log. If it fits your architecture, you know exactly how it works. If you need a distributed Redis queue, you pull insert kick directly. And you know why. Let's look at another example to see what a tailored approach can do in practice. Historically, when checking out database connections from the pool, Active Record would pin the connection to the thread. In this example, user find would check out the database connection from the pool, send a query, and pin the connection to the thread processing the request. Notice how both calls return the same adapter instance. That's the pinned connection. The next update call gets the exact same connection the previous find pinned. It might make sense at first glance, but let's now look at the following example. We've now added a call to an external service. This can be anything, an HTTP call to a payment gateway, a prompt to an LLM, or NQ in a sidekick job. With the thread pinning approach, the database connection, checked out by user update, just sits there. It lingers for 50 milliseconds, which in CPU time is an eternity. And because it's pinned to this specific thread, no other request can use it while this request waits for the external service to respond. Active Record fixed this in version 7.2 in August 2024. They updated it so that the connections are returned to the pool immediately after the query finishes, rather than hanging around for the rest of the request. Rage rolled out this exact behavior for Active Record back in March 2024, 5 months before Rails, and supporting Active Record 6+. It was possible because of the architectural choices we just talked about. Rage owns its execution model from start to finish. because we explicitly embrace a fiber-based runtime, and because we own the fiber scheduler itself, we can easily track blocking calls. Rage knows exactly when you're waiting on a network request, and it silently slips the database connection back into the pool. No abstractions, no adapters. Just knowing how your app actually works and optimizing for it. The same principle applies one layer deeper to the most fundamental piece of glue in Ruby's web stack, rack. Rack does for servers what Active Job does for Q backends. It hides the underlying server implementation, pretending that Puma, Falcon, and everything else have the same capabilities, which means that your server can only use the lowest common denominator. Rage has its own server. It still implements Rack. You can use your Rack middlewares. But because we own the server, we're not limited to what the Rack interface can express. Here's what that unlocks in practice. This code sets a persistent SSE connection and attaches a name stream to it. From anywhere else in your application, you can then broadcast to that stream. Now, imagine your Rage app is running on one server in 3 processes. 2 clients connect to the same stream in processes 1 and 2. A webhook hits process 3 and broadcasts to that stream. In Rage, it just works. Rage processes talk to each other. No Postgres, no Redis, no PubSub adapter. The broadcast from process 3 reaches processes 1 and 2 directly. This isn't possible through standard Rack because Rack doesn't know your server can do this. And it's the same pattern we saw with connection pinning. When you own the layer, you can optimize across it. When you hide behind an abstraction, you can't. And this isn't theoretical. I ran a test on a cheapest $22 a month Hetzner server. One endpoint reading from a SQL database and from a SQLite database and rendering JSON. Another holding persistent SSE streams, sending a message every second. The app was able to handle 5,000 requests per second and 5,000 concurrent SSE streams at the same time. And the more important part here is the comparison. Without the SSE streams, the same app was able to handle 11,000 requests per second, meaning that even while maintaining 5,000 active long-lived connections, the app still had half its capacity free to serve normal API traffic. That's what graceful degradation looks like when your concurrency model doesn't fight your workload. Right, so by now I've used the word fiber several times, and it's about time we talked about what that actually means. Yeah, I'm kidding. There's nothing scarier than a Rails upgrade. So imagine our app is running in just one thread, and we need to process 5 of these create requests. What happens is straightforward. Requests are processed one by one. The first request checks out a connection, sends a query, gets a response. The second request starts, and so on. And if you're thinking, that doesn't sound right, we don't want to process requests one by one. Here's the thing, that's exactly what we want. Because the alternative is threads sharing memory. And that means locks, contention, and an entire category of bugs that are hard to reproduce and harder to fix. With one thread, none of that exists. Nobody else is touching your state. The answer to what is another thread doing right now is always nothing. There is no other thread. So single-threaded execution is actually a feature. After all, Ruby is about developer happiness. But let's look closer at what our request is actually doing. Most of the time, our app is blocking. It sits there doing absolutely nothing. It computes for a fraction of a millisecond, hits the database, and then waits for the network packet to come back. And that's a crucial insight into what fibers let you do. They let you efficiently do nothing. The best way to think of a fiber is as a dedicated execution context. Not a coroutine, not a lightweight thread, a context. What happens if we wrap every request in its own context? Well, on the surface, nothing changes. We still have one thread, still processing requests sequentially. But under the hood, Ruby now intercepts blocking calls and delegates them to a construct called the fiber scheduler. How does Ruby know what to intercept? Well, when Ruby 3 was released, the core team went through all the native methods, things like reading from a network socket, writing to a file, or even just calling sleep. And added a simple condition. Whenever your code hits one of these blocking methods, Ruby checks, is the fiber scheduler registered right now? If there isn't, it blocks the thread just like it always has. But if there is, it delegates that wait to the scheduler. So the fiber scheduler is the crucial piece that makes this work. It has a set of hooks that Ruby calls for different types of blocking operations. The most important one is IOWait. Let's see how simple it actually is. When our user create call sends a query to the database, Ruby hits this hook. The scheduler looks at the current fiber and says, OK, I see you're waiting on something. Let me put your name on a list. Then it calls fiber yield. Technically, fiber yield passes control back to wherever the fiber was started. But conceptually, I want you to look at fiber yield as a simple return statement. By hitting fiber yield, the current request effectively pauses itself and politely steps out of the way. Our single thread is now free to accept the next request. The question is, how do we wake that post request back up? That's the event loop. The loop monitors all the I/O the fibers are waiting on. In this example, we are using IOSelect to ask the operating system, hey, have any of those Postgres or Redis queries finished yet? When the OS says yes, the loop finds the exact fiber that was waiting on the I/O and calls resume. Remember that fiber yield we thought of as a return? When resume is called, the fiber picks up from the exact line of code where it yielded. It doesn't even know it was ever paused. And the important detail here is what happened while it was paused. Our single thread wasn't blocked. It was immediately free to start processing the next request. The wait time of request number 1 was filled with the compute time of request number 2. And just like that, with a simple event loop, we cut out all the wait time. In about 40 lines of code, we made our application handle 5 requests concurrently on a single thread, with no thread safety concerns. And here's what matters most to the developer writing that create action. Their code didn't change. It's the same synchronous Ruby you write every day. User create, render JSON. The fiber and the scheduler work beneath the surface. So your code reads sequentially, but executes concurrently. You get the performance model of an event-driven system with the programming model of plain Ruby. So fibers let us process multiple requests concurrently by cutting out the wait time. What about the wait time within a single request? 2 calls, both IO-bound, both sequential. The request takes 130 milliseconds, even though for most of that time, we're just waiting. In the threaded world, the answer is to spin up a thread pool, decide how many threads to allocate, fire both calls in parallel, and collect the results. It works, but now you're back to reasoning about threads within your request. Rage has a simpler answer. Fiber schedule wraps each request in its own fiber. The first fiber starts, hits the network call, yields. The second fiber does the same. Fiber waits for both to finish, and while it waits, it yields too, letting other requests be processed. The total time drops from 130 milliseconds to 80, the duration of the slowest call. And it's still the same synchronous Ruby, still the same single thread. If you've ever used promise all in JavaScript, this is that, but without async or await coloring your entire code base. So I've painted a perfect picture of single-threaded concurrency. So let's talk about trade-offs. With threads, Ruby has a built-in safety net, time slicing. If one request goes rogue, maybe it's crunching a massive JSON payload or handling an expensive computation, Ruby will eventually preempt it and give other threads a turn. Your other requests keep moving. With fibers, that doesn't happen. Fibers are cooperative. They only yield control when they hit a blocking call. So if one fiber decides to compute for 300 milliseconds straight without touching any I/O, your other requests just wait. That's a real trade-off, that's true. But remember the architecture we talked about earlier? Rage can run multiple processes. Processes don't share memory, so there's no synchronization or contention, but they do know about each other. We saw that with SSE broadcasts. They form a cluster and talk to each other. So if one request in process 1 is busy crunching numbers, the requests landing in processes 2 and 3 are completely unaffected. The blast radius of a blocking fiber is one process, not the whole server. It's not the same guarantee as preemptive scheduling, but it's enough in practice. One more example. And this one is probably my favorite because it shows what happens when you take the tailored solutions idea all the way to its logical conclusion. Active Record ships with a connection pool. It's a general-purpose pool that's designed to work with threads, fibers, or anything else the community might throw at it in the future. And because it's general purpose, it's full of synchronization machinery. Mutexes, condition variables, timeout logic, all of that built to handle a case where multiple threads are racing for the same connection. But Rage doesn't have to do that. Rage knows exactly what environment it's running in, and it replaces Active Record's connection pool entirely. This is the core of Rage's connection pool, the method you hit every time you touch the database. That's it. Check if the current fiber already has a connection. If not, take one for the pool. If the pool is empty, record that this fiber is waiting, yield, letting other fibers run, and grab a connection when you're woken up. No mutexes, no synchronization at all. Because there's only one thread, there's no one to race against. The data structures are plain hashes and arrays, no thread-safe wrappers, no locking overhead. This isn't a generic pool that happens to work with fibers. It's a pool built for fibers and Active Record, and nothing else. So we've talked about the philosophy, and we've looked at specific code examples. But does this tailored, low-magic approach actually make a difference under pressure? To find out, we ran a load test on a production high-load Rails API, the source of truth for user records, accounts, contracts, authentication states. We migrated it to Rage, reproduced real-world access patterns on request distribution, and ran a stress test at 80% of maximum throughput. Now, when you hear fibers, you think of I/O-bound workloads with lots of weight on the external services. And you'd be right. But this service flipped that. It had fast database queries, but spent the vast majority of its time in the Ruby layer, crunching data with slow active model serializers. This is the kind of behavior where you'd expect threads to have the advantage. The results were surprising. Under sustained load, the Rage implementation processed 2.6 times more requests than the original Rails setup. Not a 20% bump, 2.6 times. And it did so with a significantly lower P95 latency. So the question is why? In a CPU-bound workload, where did this massive gain come from? It wasn't one single thing. It was the entire architecture working together. The efficient web server, the fiber native connection pool, the optimized HTTP router, the fiber model itself. And that's the pattern I keep coming back to. When you own the layer, when you don't hide behind generic abstractions, the code gets simpler and faster. Not one or the other, both. The complexity doesn't just move somewhere. Much of it simply disappears because it was only there to handle the case that your architecture ruled out from the start. So let me circle back to where we started. Ruby is one of the best languages for writing software. And fewer people are choosing it every year. I don't think the answer is to convince everyone that what we already have is enough. We've tried that. We've written the blog posts, we've shared the benchmarks, we've said Ruby's not dead so many times it started to lose its meaning. But I also don't think the answer is to abandon what makes Ruby great. The readability, the expressiveness, the power of duck typing, those aren't the problem. The problem is that we wrapped all of that in a single set of opinions and told developers to stop looking underneath. And it worked. But things have changed. The workloads are more IO-bound, the applications are more distributed, and developers have more options than they did 20 years ago. Rage is my answer to this, but it doesn't have to be yours. What matters is the principle that Ruby deserves tools that are transparent about what they do, tailored to their specific use case, and simple not because they hide complexity, but because they've eliminated it. That you can write plain, sequential Ruby and have it execute concurrently. That your framework doesn't need to pretend every backend is the same to be useful. Ruby's best days aren't behind, but they're not going to come from reassuring ourselves that everything is fine. They'll come from building tools that make developers choose Ruby. Not because they're told to, but because they looked under the hood and liked what they saw. Thank you.